Okay, so all right, so we were talking about APR and APY, so let's put this to work here. So here's the situation. Consider an APR, annual percentage rate, of 15%, and a $6,000 initial investment. So that means that every year your money will have a percent increase of 15%, right? Got one, yeah, there. Yes? Every year your money will increase by 15%. No, right? This is what we talked about Thursday. And did you have some homework on it? On APR? You have some APR stuff? Yeah. Okay? So, right, that's not enough information. Just saying an APR of 15% does not tell you what the true percent increase will be, right? What other information do you need to know? Well, that would give it to you. That's what it is. But what information do you need to know to get the APY?
You need to buy 15 by 12 or
how often it's compounding. We need that information about not only the APR, but combine it with a certain compounding situation. Then we can know what the true rate of increase is. Okay, what the true percent increase is. Okay, so that's what we're going to do. So here's an APR 15% with quarterly compounding. With quarterly compounding, we're going to chase this out here. So what would my per period rate be with an APR, or in this case, per quarter rate, an APR of 15% and quarterly compounding? Okay, so just kind of a new ground rule for the class. No headphones in class, okay? So you got your full attention on what we're doing. So no headphones. All right, so what will the per period rate be? Hamid?
15 divided by
4. He said 15 divided by 4. What do you think? That's it. Okay? 0.15 divided by 4. This is the one time where we don't follow our principles of exponential growth in the first step of using an APR. But now, once we have that per period rate, the rest of the math follows our principles of exponential growth, right? So I want to put that in. So equals 0.15 divided by that right there. Okay? So per quarter, and what we get? I got 0.375. Okay, so that's the per period rate, or that's the quarterly rate. What about the per period growth factor? Tim? So if that's the per period rate, what's the per period growth factor?
1.0375.
So he's saying add 1 to that, right? You take 1 and you add it to the 0.015 divided by 4. Agree with that? Yeah, we know if we have the per period, we have a certain rate of increase as a decimal, then the growth factor would just be 1 plus that. So here I'm going to go equals 1 plus that thing. And that's what we said, 1.0375. Okay, now so from that, how do I get the annual growth factor? Christina, I've got the per period growth factor right here, and our periods are 4 per year. How would I get the annual growth factor? So this is what growth factor we would have, say, for every 3 months or every quarter of a year. Right? And what are our growth factors? They're multipliers on output to get the next output. So what would my multiplier be for a whole year? It's 1. What's that? 4? How do we get the annual growth factor from the quarterly growth factor? Anna? To the 4th, because every quarter you would multiply by this number, right? So then by a year, how many times will you have multiplied by it? 4 times, right? So over the course of a year, if you're multiplying by this, to get the new amount every quarter, then at the end of a year, you have multiplied by it 4 times. So it's 1 plus 0.15 over 4 raised to the 4. Let's do it. So it'll be equals that thing raised to the that thing. Okay, so the per period growth factor raised to the 4th. Oh, what happened?
Probably just put 4 instead of raised to the 4.
What did I do? No, that should work perfectly well. What's going on?
Yeah, you did. Is there an F on?
Oh, I didn't get it all the way over. There's the F is this skinny one to make the lines right. Okay, thank you. Very good. Okay, so it's going to be this. There we go, E6. All right. Okay, so what is the APY? What's the APY? Diana. She wants 15.87. Agree with that? Okay, and why isn't it 15? So what is APY? What does that mean?
Annual percentage yield.
Annual percent yield, right? And how did you get the 15.87? Diana, tell me how you got it. What's that? You just saw it. So what math could we do to get that 15.87? What could we do first to that? How would we get to that? So we did some math on that. What would you do first? Jared? Subtract 1. This is what you're doing in your brain. You just didn't know it, right? So you subtracted 1, and then what you do? Which is what operation? We multiplying by 100. So that's what you did just by looking at it. 15.87. So 15% compounded quarterly, what does the 15.87 then mean? If it's 15% compounded quarterly, we get this other number, 15.87. What is that? Brooke? What's the meaning of the 15.87? The difference between, what did you say? Great. Okay, who can explain the difference between APR and APY? I know someone knows. Justin, can you talk about what's the difference between APR and APY?
I'm actually not quite sure myself.
Okay, we came to the right question. Shola, any ideas? The whole year. What do you mean the whole year? What about the whole year? If it was a loan, right? So, right, it's the percent. The key about APY this is the key. It's the true or actual percent increase. APY is the true percent increase. APR, it's just not enough information. It's kind of something like the true percent increase, but you need the compounding along with it to establish what your true percent increase is per year. It's your actual percent increase. Okay, so why is it higher than 15? If the APR is 15, why is this higher than 15? Taz?
Because instead of it, you're just compounding once every year.
Okay.
4 times.
Compounding 4 times. So we split that rate up into 4, that 15 into 4. We calculate the interest at the end of 3 months, and we put that interest back into the account. And then we let that total amount grow another 3 months. And then we take the interest on that, and we put it back into the account. So every 3 months, every quarter, We calculate the total interest based on this quarterly rate, put it back into the account, and let it grow some more. And so what's happening, the interest is growing on the interest. And then the cumulative effect of that is that we get a little bit more than 15% because interest grows on interest throughout the year. In this case, 3 times. Does it make sense? Is it better? Yeah, okay, cool. All right, so what's the T-year growth factor? T-year growth factor, Austin. So the annual growth factor is this one here. What's the T-year growth factor?
1.1587.
He wants this one to the T. What do you think? Yep, you're going to take the annual growth factor, multiply it together, T times. So we got, that's our annual to the 4th, and then we're going to take that and raise it to the T. There's our 1-year growth factor, or T-year, for T years. Okay, so now we've got the T-year growth factor, and we have a starting value of 6,000. How would we get how much that 6,000 is worth after T years? Patrick?
We would use that formula, but use the initial value for that formula.
Okay.
6,000.
So take 6,000 and do what?
Put it into that formula for our initial value.
I got all numbers here. Where would I put the 6,000 in? You want to put it into this? I've got all numbers, right? And T is a number of years. So this is the T-year growth factor. What does it mean? What does it do? What does the T-year growth factor do? What does any growth factor do? Uda, what does a T-year growth factor mean? Yeah, it's a multiplier. So if I got 6,000, I want to know how much that's worth T years later. What do I do? Yeah. That's it, right? So T-year growth factor. It's a multiplier on output to give us another output, right? That's why we've been hammering this for 2 weeks. It's a multiplier on output to give us another output. So this is the multiplier on output, in this case, a starting output of 6,000. And when we make that multiplication, what will we get? The new value T years later, right? Okay, so it would be 6,000 times, that's times, the T-year growth factor. 1 plus 0.15 over 4, all to the 4th, all to the T. Okay, does it make sense? So this is all kind of putting together stuff we've already learned. Everything here we learned Thursday and before. We're just putting it all together. So notice how it was all about growth factors. Building up from the period rate, it was all about growth factors to get something that would give us a final value of the account, right? Final value of the account given an initial amount. It's all about building up these growth factors. Okay, so as I take attendance, you're going to work through these these rows, monthly, weekly, and daily. The key is I want you to practice setting up these expressions. Not only finding the values that I've done with a spreadsheet, but what I've written in blue. Okay, so I want you to practice writing that out, what I've written in blue. And keep asking yourself, what does this number mean? What does this number mean? What does this number mean? That's what we're after. Really understanding all the values. Okay, so hopefully, here. Okay, you can check your values for monthly, and then I'm going to call on somebody and have you take me through the setup for those. So check your values. Okay, Audie, how did this go for monthly?
You took 0.15 for the recall, because you actually won.
Right, okay. Keep going. You're on a roll.
I didn't do any of the numbers, I just put answer 1, 2, 3 in the flowchart.
Well, how would you do the mathematics to get this number here?
That's the thing, I didn't have the number, but I could take the value and add it to 1 and it'd be that.
That's what I mean, add it to 1.
So you add 1, 2, that's what we got.
Okay?
Here's answer 2. You take that, you raise it by the number of periods, which is 12.
Okay, so those are per period. So per period, this is our monthly multiplier, right? If that's the per period growth factor, that's the monthly multiplier. And so he wants the annual multiplier to be, you said, raised to the?
To 12 months.
Yep. So if you multiply that monthly multiplier together 12 times, it would be the same effect as a 1-year multiplier, right? That's our annual growth factor. Okay?
Then you just you take 1 away from that,
Right?
and then it gives you the. Well, then you multiply that by 100, it gives you the percent.
Perfect. Right. So we can see it there,
Yeah.
or we can just subtract 1 and multiply by 100, and there it is. And what does the 16.08 mean? What does that mean? Nadine?
It's a true increase of the 6,000
It's the true increase.
2% increase of the yield percentage yield.
Right. So if you take this APR of 15% and compound it monthly instead of quarterly, now your true yield is a little bit higher than what it was quarterly, right? It went up to do monthly compounding instead of quarterly. It went up from 15.87 to 16.08. You had a question, Audie?
Yeah. So they do this just to see like the best option for the investment.
You mean this? Why they do it this way? So
Yeah.
the reason they do it this.
They see the APY as being important if you compound it differently. So if you're trying to make the most money, you know what I mean?
Yeah, if it's an investment, then you're interested. Well, no matter what, but you're interested in the APY and having that be as high as possible. If it's an investment, because that's the true annual percent increase of your money. If it's a loan, you want this to be as low as possible, right? Because that's the interest you're paying. Okay? Yeah. Okay. So how about the T-year growth factor? Let's go with Joe. Did you get the T-year growth factor for this one?
Should be 1 plus 150
Yep.
over 12
Yep.
is 12.
Raise the 12, right? Raise the T. Okay, so that will be our T-year growth factor. And then how would we find the value of 6,000 after T years, this case? Corey?
You'll multiply 6,000 times what's put before.
Right. Because that's what these growth factors do, right? They're multipliers on an output value to give you a future output value. In this case, T years later. It gives you the output value T years later. It's all about growth factors. That's what we said from the beginning. Okay. Nice. Okay, so weekly, quick. Who can take me through it? Walter, did you get weekly?
Yeah, I provided 0.15 divided by 52 and
Good.
0.002884.
Okay. Let me put the numbers in first. And then we'll do the calculations. .002884. Good. Okay. And what did you do from there?
I added one.
And can you explain when you add 1 to that number over here? This 1.022. What does that number mean? What is it about?
The growth factor.
What growth factor and what does it do? Which growth factor is it?
Period growth factor.
Yep. And our periods are
Weekly.
weeks. So it's a weekly growth factor. It's a weekly growth factor. And so what's the annual growth factor?
You take that and you express the power of 52.
Who can explain why? Why do we raise that to the 52nd power? Brian.
This is being compounded weekly, multiplied by itself 52 times.
Multiply it by itself 52 times. So if that's our weekly multiplier, if we want a yearly multiplier, we need that weekly multiplier multiplied together 52 times. So that gives us the yearly multiplier. Okay? APY 16.16, is that right? T-year growth factor. Jared.
You take that annual growth factor
Uh-huh.
and bring it to the power of t.
So take that whole thing, divide by 12 to the 12.
52.
52? Just kidding? Just checking you? To the T. Value of 6,000 after T years. Malin, how to get the value of 6,000 after T years? That's it. 6,000 times T year growth factor. Okay, if you want to check your work for daily, here it is. Questions on this process? Doesn't make sense. Okay, so let's generalize it. So we're going to generalize it. So now the APR is anything, R. We're going to compound n times per year, n, and initial investment of P. Do it again, do it one more time. So what will your per period rate be? What will your per period growth factor, your annual growth factor, T year, and value of P dollars. So if an APR of R with n compounds per year, and initial investment of P, see if you can do it. Same thing again, but just now general, using variables instead of actual numbers. It's not 1.5 anymore. APR is R. APR is R. Start. Questions? Makes sense. Did you get it? Good. Okay, how'd we do? Alex, did you get the per period rate?
Per period rate, yes.
Tell me.
You're going to have your APR, which is R,
R?
over your compounding period, which is N, well, the number of compounding, and GR.
Yeah, and this is decimal. So this is decimal version. Okay, so decimal version of the APR. R over N, he said. What do you think? Austin, take it from there. What's the per period growth factor?
1 plus R over N.
1 plus R over N. Annual growth factor. Jonathan.
It's 1 plus R over N. 2 N.
That's it. All right, T-year growth factor. Morgan.
1 plus R over N to the N and to the T.
That's it. Value of P dollars after 2 years. Diana, did you get it? Okay, so we have it totally generalized. Any starting amount, any APR, any number of compoundings per year, any number of years. Okay, this will find us the final value of the account. Okay, and so we can make that a function of the number of years, which is the most common thing to do. So A is the final value. And that's equal to our initial amount. Again, same thing. Okay, and so this is called the, the compound interest formula. But before you just think, oh, when you hear the word formula, it's like, oh, great, I'm set now. Don't have to really think. I can just use the formula. Think again. Okay, compound interest formula. So you'll be responsible for understanding how we made it, right? So this process here, what everything means along the way, you got to know that stuff. You will be tested on that, okay? So not only be able to use it to calculate final values of an account, but know that it's all about growth factors. How many growth factors do you see in this formula? How many growth factors exist in that formula?
3.
Hamid,
3.
tell me which ones they are.
1 plus R divided by N.
1 plus R over N. Which growth factor is that?
First, the period rate.
It's not a rate.
The period growth factor.
Period growth factor, right? Okay.
The period growth factor raised to N is the annual growth factor.
Annual 1 year, right? That's the 1 year growth factor, right?
The annual growth factor raised to T is how many years we have?
That's how many years? When you raise it to the T, you get how many years?
2 years.
Yeah, but what is that number when you raise it to the T? It's not how many years. It's a growth factor, right? It's the T-year growth factor. Yeah, so there are 3. Like many of you said, there are 3 growth factors embedded in that formula, and we know what that all means, right? So it's like review to put that thing together. And you have to know that. Questions? So maybe in a previous course, like a high school course, you've seen this, you've done compound interest problems before. But I would guess that now you have a totally new appreciation for it because we see that it's just based on growth factors, okay? So that's pretty cool. So let's go back to the other page. And I want to examine these APYs. So what happens when you compound more often? Obviously, what's happening if you compound more? What happens to our actual rate? Increases, okay? So can I do better than daily compounding? Can I compound more often than that?
Per year.
per hour. Can I compound more often than that? Per minute, per second. Can I do better than per second? Per half second, per tenth of a second, okay? So what's the best, or not best, but what's the most I can compound in a year? What's the most number of times I can compound in a year? If I can always, whatever time I pick, a second, a half a second, a millisecond, a microsecond, I can always make it less, right? And so how many times are we talking about then? Lots and lots of times. It's kind of, what? What do you mean constant? Oh, right, yes. Yep, exactly. And so how many times, if it was doing that, how many times in the year would you compound? Right, like an infinite. So it's kind of like we're talking about n being infinity, or n, what we call increasing without bound, getting really, really large. And he said constant, and that's right. It says constant compounding, but it's actually the technical term is continuous compounding.
Do companies actually use more than daily?
In terms of use, it would depend on what you're using it for. Like, I think mostly like with car loans and home loans, it's like monthly. But in other applications, I don't know if they use daily. I think credit cards use daily. Sometimes they use daily compounding for credit cards. So continuous compounding means that our n value is just getting really, really large. Okay, and what was I going to say here? So if we, which just means like every moment. Compound every moment. So what do? In a teeny little moment of time, we calculate that teeny amount of interest and we add it back in. And in the next teeny little bit of moment of time, we calculate that teeny little bit of interest, add it back in. We do that every moment for the whole year, okay? And so that interest keeps building on the interest, little teeny bits at a time, all the way. Okay, so if we do that, then that means this APY is just going to get infinitely large, right? No. What do you see? How do you know that that's not going to happen?
And video they showed it, like one of the videos, and there's some sort of like what I call limit.
Okay, that's right. It's limiting value. How do you see that in the numbers here? How do you see it in the numbers here? Yeah, Patrick.
Well, you can see it when they change from weekly to daily.
Yeah.
It increases by a small amount.
Really small percentage, right? So let's make a guess. If we compound it continuously, what do you guess this number is going to be? 18? 16.5? No, what do you think?
16.182.
Yes, it's going to be something just a little bit higher than 16.18 based on what we're seeing here, right? The more often you compound, yes, it goes up, but it goes up in much greater, much smaller and smaller increases, right? So it's leveling out pretty. So he wants, what'd you say? Did you already do it?
No.
Okay, so he's guessing
16.182, probably smaller than that.
16, this is what he wants to guess, 16.182. So let's see, that's our guess. Okay, our guess is 16.182. All right, so how do we get that? So when we look at our interest formula, so this was 1 plus r over n to the n to the t times p. Shoot. Be over here. Okay. So there it is. So what happens when n gets very large without bound? You guys saw in the video with this expression right here. As n gets really, really large, if that r was a 1, then that number in there would be As n got very, very large, if r was 1, what number do we get? Should remember E, right? So E. And E is, I'll write it up here, 2.8. Dang it, I've missed it all day long. What is it? 2.7. 2.7. 1828. 182. I don't know very much of it. 49045. Okay, there we go. I've got a trick to remember it. Andrew Jackson was the 7th president. He served 2 terms. The first was in 1828. There's his 2 terms. And the rumor had it that he lived to be 90 years old, and he wore a 45 on each hip.
It's an inside joke.
You can laugh, but I know more places of E than you. Okay? So, but the point is that it's a number, right? It's like pi, okay? It's like pi. 3.14159, blah, 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 right? So infinite, non-repeating decimal. E is just like that, and it turns out it's what's called the natural base. Natural base. Okay, so this, as n gets very large, if r was 1, then that thing becomes this number E. All right, but we have an r, so instead of e to the 1, it's e to the r. So everything in those brackets there, when n gets really, really large, or in other words, continuous compounding, everything in those square brackets is e to the r. But we still have to the t, and we still have the p. So this is the alternate formula when you have continuous compounding. Any other compounding, it's this one. Continuous compounding, we need this one here. Now check this out. This kind of brings us full circle back to our old school exponential formula. What was our original exponential growth formula? I'll do it in red. So we said y equals, what was our original exponential growth formula? We should all know this. What's that? He wants a b to the x. Is that our exponential growth formula? A, b to the x. And when we look at that, like spread out, okay? That x is the exponent on b. So when we look at that, how do we get our goal is the APY. How do we get the true percent increase looking at a times b to the x? What do we look at to figure out the true percent increase? Tim, where are we going to, if we knew a, b to the x, what would we do to get the true percent increase? Not sure. Where does percent increase come from? Anna, do you know? Oh, okay, real basic thing here. How do we get, what's the centerpiece of a, b to the x, our exponential growth? What's the centerpiece? B, the growth factor, right? And from the growth factor, we can get percent change, right? Easily. So this is our source of percent change. Notice that this compound, this continuous compound is in the same form. What is our A? Initial. What is X? Input. So what is B? But what is it in this? E to the R. Here's the key. B equals E to the R. So with continuous compounding, E to the R is the 1-year growth factor. 1 year, or the annual growth factor. And from the annual growth factor, we can get APY. So how are we going to get the APY in this situation? APR of 15%, 6,000 initial investment. How can we use this to get our APY? What can we do? Justin. Okay, so you want to calculate e to the r?
Yes.
Yeah, so calculating e to the r will give us b, the 1-year growth factor. And then from that, we can see what the So, and your calculator, it's over on the, most of you have a TI, or on the left side, you'll hit second and then LN, which is right next to 4. Second LN is the E button. And it'll give you a caret because it's expecting an exponent. What exponent are you going to put in for this one? And what are you going to put in? 0.15, 15% is our APR, right? That's our value of R. So you're going to go E to the 0.15. Are you going to get a rate for that? Is that going to give you a rate? What's that going to give you? Annual growth factor, from which we can easily get the rate. So what is that? If you do E to the 0.15, you get 1.16. And we can see how good Audie's guess is. 1.6, 1.8, 3?
Yeah.
Off by 1,000th. B plus. 1.16. Sorry, this is the rate here. So it got the growth factor for continuous compounding now is 1.16183, which makes the, just put it in, 16.183. Can't do that. Erased. All right, so that is our APY for continuous compounding if the APR is 15%. Any questions? Did you catch all that? Okay, so let's, so why don't you find the APY for continuous compounding at 8.5%. So if the APR is 8.5%, what is the true rate of return? Find that for 8.5%, compounded continuously. Can I erase what's on the screen? Anybody else need it? So what did I say? I said APR was what? 8.5%. What kind of compounding do we have? Continuous compounding. Get me started, Christina. What's that? Oh, all I want to know is the APY. I just want to know what my APY is. What does this truly mean for an annual percent increase? I don't need the 6,000 for that. Let's see. Jared Smith. How am I going to figure out what the APY is for 8.5% continuous compounding? Yep. And that's right. N goes to infinity. So how do we do it? Shola, you know how to do this? Where is that going to come from? Diana, do you know? Good. Because that's our e to the r, and that equals to? 1.0887. And that's b, right? Because we're looking at p e to the rt, and we're saying it's basically the same thing as a b to the x, right? So what's b equal to? E to the r. That's the key. B can help us find the true rate of return per year, the APY. Is it the APY? Is B the APY? Patrick, what is B? What does that mean?
It's the growth factor.
That's the annual growth factor, and from it we can get the true percent increase. Okay, so tell me then, what is the APY? 8.872. Okay, versus the APR was 8.5, right? So continuous compounding at 8.5% actually makes a true percent change of 8.872.
Is that the limit as to how much you'll get?
That's the best you can do because you can't compound any more than every moment, right? Exactly. The best compounding you can do is every moment. So that's the limit. Exactly. Okay, so how about compounded monthly? So what would the APY be? Same thing, compounded monthly. So 8.5%. Can you figure out compounded monthly what the APY will be? So that's what we did at the beginning of class. Can you do it? So now we want APR of 8.5%. All right, before we do it, is it going to be less than 8.5% between these two or greater than this one? Will it be less than 8.5 between these two or greater than this one? Brooke says between. Okay, can you do it? What will the APY be? So you had homework like this, right? Nadine, did you get it? Tell me what you did. Tell me your process.
So it's 0.085 divided by 12,
Good.
and then you add 1 to that, which is, you get 1.0070.
Okay. And what would that number mean? What is that number?
That's the growth factor
For?
for the one, or the APR for 1 month. The growth factor. The period growth factor.
The month, right? The growth factor for 1 month, right? The growth factor for 1 month.
And then after you add 1 to that, you'll raise it to 12,
Good.
and then you take 1 from it.
Yeah. What'd you get when you did that?
The percentage is 8.84.
Like this?
Yeah, 3.9. It'll be 3.9.
Oops. Sorry, not percent. Okay. So APY. 8.84%. Better than the APR, of course, but not as good as continuous. If it's a better, so if it's an investment, it's an investment. Okay, questions on this? Please, Alex.
Would it be 0.085?
Yes,
1.08.
Growth factor.
Over 12. It's the 1 over 12.
Yeah. Your monthly rate.
Oh yeah, just forgot 0 in there. How about that? Okay, is that good? Cool. But the rest of the numbers all right? Okay, so here the idea here is that from here, this idea of continuous compounding can be applied to any exponential growth situation. Any exponential growth situation. So let's look at that. So, okay, so what I want you to do is, there's 5 letters there. A, P, E, R, and T. So get a partner and talk about what each of those letters represents. What do each of those letters, exactly what quantity do each of those represent? Go.
A will be the whole thing.
Okay, Tim, tell me what A is. Final value. Keep going. What's P? What does that mean? Initial, right? So it's initial amount. And so, yeah, initial amount, and that has a special name called the principal, right? So that's why it's P. But that we know that's the initial amount. What about E? Omar.
Oh, A is the, well, E to the R is the...
I want to know what E is.
E is the number, that 2 point...
That's right, exactly. It's a number. Exactly right.
2.718.
2.718, blah, blah, blah. Okay, that's a number. So, and then, but that's good. What is E to the R? E to the R is?
E to the R is the growth factor.
That's the, right, it's the one annual growth factor. What is R, Morgan?
R is what would be
APR.
decimal.
In decimal form. Excellent. Okay, and T. Keep going, Morgan.
Oh,
Yes, the input. Is that what you said?
yeah.
It's the easiest one. So what does the input represent here? Number of years. Okay, so just remember that continuous rate R is not the true percent change. R is the APR. Not like an APR. It is. Okay, R is the APR. Only when that R is combined with continuous compounding can the actual percent change be known. So now the transition is that all these other applications of exponential growth, like we've been talking about populations and the way things decay or grow, okay, we can now see those things through this lens of this idea of continuous compounding or continuous rate. Okay? So let's see how we do that. What was our general exponential formula? F of x equals a b to the x, right? A b to the x. Well, now we can write that in a different form. A e to the kx. So that's kind of like we're stealing from continuous compounding. We're saying let's apply that to any situation, not just money. Well, let's apply this formula and look at it when you're talking about anything, not just money. And now, so instead of R, we'll use K. And so K is what we'll call the continuous rate. Okay, so let me just warn you. This one of the things students struggle with the most. So try to tune in, really have your brain on. K is the continuous rate. So you got to look for that language in problems. When it gives you a percent, if it says it's the continuous rate, is it the true rate of increase? No, it's like APR, okay? K is a number just like APR. You have to combine it with continuous compounding, and it gives you something else for the true rate, the true percent increase or decrease. Okay, so how do we find true percent change? In all this stuff here, where does the true percent change come from? How do we calculate the true percent change? Austin, do you know? No, okay, we better. Fuda, in all this stuff here, where is the true percent change found, or how can we get it? Not sure. Nadine? E to the kx. Not quite. Taz? Which is the same as? B. Okay, so the A's are the same. The X's are the same, which leaves B is e to the k, and that's B is our key. B is our link to true percent change. We've been working on it for 2 weeks. We're working on it for 2 weeks. So if we had the continuous rate k, we can figure out the true percent change by applying this, by getting that value of B. If we got that value of B, then we're there. We just use what we learned before. Okay? So B is the true growth factor for 1 unit of x, which reveals the true rate of increase. That's what we're saying. This is a really hard idea for students. They really struggle with this. Okay? So let's practice. Let's try this. Can I go on to the next screen? Yeah. So this is what I'm showing you right here is the key to understanding the next thing we're doing. So there it is again up at the top, okay? Same thing up at the top. B is the same as e to the k. K is called the continuous rate. And B is the true growth factor. So notice, K is a rate. It's like an APR rate. We call it the continuous rate. B is not a rate, it's a growth factor. It's the true growth factor, the centerpiece of exponential growth. So they're apples and oranges. K is the rate, but it's not the true rate. B is a growth factor that can give us the true rate. All right, so let's try this. Suppose a nation's population has a 1-decade continuous rate of 19.2%. Can you figure out the true percent increase per decade? And then as a follow-up question, can you figure out the true percent increase per year? So did you catch what's going on? Can you do this? So what's the true percent increase per decade? Is it going to be more or less or the same than 19.2? Should be more, right? Because we're going to apply, the idea is we're applying continuous compounding to the continuous rate, and that gives us the true rate. Can you do it? And then from there, a review question, can you get the true percent rate per year? That's a review. Yeah, just the year used. We'll think about that later. So everything's in decades, right? Everything's in decades. Here's the key. B is the true growth factor for 1 unit of x, revealing the true rate of increase. That's the key. If you understand that, then if you want the true percent increase per decade, you're going to get that value of B. Jonathan, did you make progress on this? What'd you say? So what, of all this stuff up here that I've got, what is the 19.2%? What is that? Is it F, X, A, B, E, K? What is the 19.2? Jonathan, do you know? Can you identify in all this stuff up here, can you identify what the 19.2 is? K, right. So can we do it as a decimal? So K is as a decimal?
0.19.
Beautiful. Okay. How can we use that K value, the continuous rate, to get the true percent increase? Keep going.
You do e to the k
Yes.
per decade.
Yeah, everything's in decades. So, did I say year? Sorry, everything's in decades. And what did you do that? What'd you get?
Oh, I got 1.2116. Or 7.
Okay, and how does that help? What is that? What is that number? What does that mean?
Yeah, it's the continuous for 1 year, right? I mean, for a decade.
What is that about 1 decade? What kind of number is that?
It's a good factor.
Growth factor. It's the 1 decade growth factor. And we want the 1 decade percent increase. You're doing great. Keep going.
So I just to the 110.
So how do we get percent increase from growth factor?
Oh, it's still 1.
Yeah, what is it? So 19.2% with that's as a continuous rate is a true population growth of 21.17% increase. What about per year? Brooke. Good. Good. And you got? Percent increase per year? Right, so to get the per year percent increase, we got to go through growth factors to do it, right? We did that last week. Growth factors, 1 decade growth factor, 1 year growth factor, 1 year percent change. Okay, function that outputs the population T decades. After the nation had 23,168 people. Justin, did you get it? So we'll say P of T.
So would the initial be 230, 168?
Okay.
And then times 1.2117.
Okay.
To
Is that one way to do it? Okay, Patrick, what's the other way? Did you get that?
I didn't do it the way.
Yeah, Alex.
You could do your same initial values, and then you put it times e to the 0.192
Okay,
times t. I mean to the t.
excellent. So those two are the same function. Those two are the same function. Okay, there's one more example I want to do. It's I'll just go do it quickly, okay? Any questions on this one? Are we good? If I can find it here. Okay, what I'll do is I'll put it on the video because I got to it in the other class. So I'll tack it on at the end of the video. And there's just one more example, which is important because it's continuous decay rate. All right, which is a little bit harder. Homework for Thursday, no web work. I've posted problems from the workbook, but it's a long list and they'll all be due Tuesday. So get started early. So don't wait all the way till the weekend. Get started early. It's a long list. And then if you got your quiz, Thursday quiz. Yes, the homework I put for Thursday is actually due Tuesday. You'll see. Right. There's no written homework you'll be turning in Thursday. I'll show you what it looks like. Hi.
So today is February 20th.
Fifth.
So this for Thursday, right?
Yep.
Do you,
You have recitation today or Thursday?
it's today.
So your quiz is today.